So, chapter 4 is the chi-square test of independence. It is very much a next step building block to what we've already seen, so it's not going to be like it's a totally new process. This is a part of what we call non-parametric statistics. So, what you guys have learned so far when we're testing for independence is there's been this common assumption shared that data is being analyzed and calculated from a sample drawn from a normally distributed population. So that's the assumption we've had to make for every single thing that we've done to date. However, in the real world, outside of our classroom, that's typically not the case. So most of the time in math, we find there's things like air friction and things like that come into play. Same is true in statistics. So when we're doing real world stuff, we're making a lot of assumptions. So populations can have skewed distributions. For example, like the population of the US, the age is very skewed. We're not normally distributed in age. And so the normal distribution assumption doesn't apply in those cases. So there's a subgroup of statistics that we can use when we do not assume a normal distribution. And we call that non-parametric statistics. So the chi-square test for independence is one of the most commonly used ones, and it's really the only one we're going to study in depth. This test is used with two categorical variables, so two categories, small, medium, large, gender, marital status, eye color, hair color, those things that are categories. And it lets you determine whether cases in a sample fall into categories that are proportions equal to what I would expect by chance. So that's kind of basically the workaround to the assumption for the normal distribution is we're assuming the proportions would be equal to like a random situation. So an example of when to use this. So let's say that there's a summer job at a pet shop and you want to know if boys and girls differ in what they choose for pets. Notice pet is categorical, gender is categorical. To conduct your study, you must randomly select 50 girls, 50 boys between the set ages of 5 and 10 who visit your shop over the summer and record the animals they choose for their pet. Now, 5 and 10 age is not a variable here. That's just limiting the population that I'm looking at. So don't confuse age with a variable. I'm still just looking at gender and pet. The data you collect is in the table as shown below. So I've got a nice little table that shows me who selected each thing. So the formula for chi-square that Excel is going to do for us is the formula given there. And so it's going to work by comparing the categorically coded data. So what that means is a lot of times we say males are number 1, females are number 2. And so instead of typing male and female in, we type in 1 and 2 or 0 and 1. And then for the pets, we would make 1, 2, and 3 equal different pets, and we would enter those in. So that's how we're kind of converting categories to numbers. And so once we do that, it allows us to determine whether the observed frequencies are significantly different from what we would expect by chance. So just like our t-test and our f-values, there are family distributions that let you calculate the significance of chi-squared, and we're going to use Appendix E. So like I said, we're building on what we've already done. We're going to follow the process. We're going to calculate the chi-squared observed value, and then we're going to use Appendix E to work with it. In a chi-square test of independence, my degrees of freedom is going to be r-1 times c-1. This is very different. So I have to go back to my table and look at the number of rows and the number of columns with data in them, not with titles and things. And that's what I have to use to calculate the degrees of freedom. So that is a little bit of a different calculation. So if I want to actually calculate the value, we're going to calculate the expected values for each cell. So for the girls and puppy cell, we divide by the total number of girls in our sample, by the total sample size, 50, by the total sample size, 100. So let's look at the original table. So I have girls, my row total is 50, and so that's what I'm dividing by to get things there for that total 100. So there's 50 and 100, that's where they're coming from. And then I'm going to divide by the total number of puppy purchasers by the total number of the sample. So puppy purchasers by the sample size here. So we had 33 puppy purchasers. That's and I'm going to multiply those fractions together. So that's why this isn't like 0.3 or 0.33, because I have to do that calculation and multiply them together, which sounds complicated, but it would just be this right here. So I have 50 females out of 100, 33 of them pick puppies out of 100. I take that calculation and then I convert it to basically a percent by multiplying it by 100 again, which gives us 16.5. So that would be what we would expect to see by chance. So Excel is going to do this with you, but you're going to kind of need to understand what it's doing here. So I'm going to follow that same procedure for every cell. So for boys, I would have to have the total number of boys, which is 50 over 100, times the number of boys that purchased a puppy. So if we go back to our original table slide, the boys that purchased the puppy was 23. So I would multiply that by 23 over 100 and then multiply again by 100 to get the 16.5 for boys. Once I have all of those expected values done, I'm going to have to do another calculation with them. So I'm going to enter those expected values and observed values into the formula. Expected values is going to be E, observed values is going to be O. Again, Excel is going to do this formula for us, but we still need to understand where do we get the numbers to plug in. So now that we've gotten those numbers, we're going to compare these with the values collected in my study to see if they're significantly different. So according to the chi-squared formula, I'm going to plug those values in, sum the frequencies. Again, Excel is going to use this. I'm going to choose an alpha value for appendix E, and that for this we could use 0.05 because it's not medical. It's not something that needs a higher alpha level. And then I'm going to determine the degrees of freedom. So it's kind of a lengthy process. We're going to have a couple of iterations happening in Excel to make this happen. And then I'm going to interpret the results based on what I find in the appendix and if the value is greater or less than the alpha significance. So what we find is, if we actually look in the appendix, we see that the critical value with 2 degrees of freedom calculated from the rows and columns is 5.99. So when I compare that to my observed value, which is 12.18, and our critical value, I see that the observed is larger. So therefore, we're going to say there is a statistically significant value, just like always. So anytime it's bigger, we always say, yep, it's just statistically significant. So we can conclude the selection of the first pet is contingent upon or dependent upon the child's gender. So you're proving that one thing depends on another with chi-squared. And there's our summary slide. So chi-squared isn't too bad. It's a bit more calculation than we're used to with the t-test, but Excel is going to be able to help us get to those calculations. And if not, you can use a scientific calculator to work with the fractions. So it's not going to be an overly burdensome calculation like it might seem from seeing that many slides of formulas.